Hello to everyone, and today I'll be discussing that the quantum theory of the Raman effect. And in the last class, we have discussed the classical theory of the quantum Raman effect. And there are a couple of disappointments from the classical theory of the Raman effect, and it will be sought out with the help of the quantum theory of Raman effect. Now, the electromagnetic radiation, which is quantized, which is at the bundle of the photons, and if I have a bundle of photons or this having the wave number nu and wave number nu, and the energy of hc of nu falls in a scatter or the molecule, and it scatters from that molecule or the scatterer, then there are three possibilities. Number one, that collision may be the elastic collision, and just it deviates its path, and we are observing that there is no shift in the energy. In output, this scattered photon, which is scattered from this molecule, which is the elastic collision, there is no shift in the energy. Then at the output, we are getting the same frequency, that is same wave number, that is the nu. So these are called the Rayleigh scattering or the Rayleigh line. So in number two possibility is that you may have a collision is an inelastic. In an inelastic, it may gain some energy or it could give the energy to the photon. So suppose initially I have a molecule in an energy level of E double prime, and it gets excited, takes the energy from this photon h nu of c, and it de-excited to the energy level of E single prime. So the energy of the scattered photon is h c nu minus delta of E, and which is obviously this is the less than to this incident photon. And if I will represent in a term of the wave number, then the wave number of the scattered photon is hc nu minus delta E divided by hc. And this is the total shift in the energy is delta E divided by hc. And this shift in your wave number, as it is a lower side of this Rayleigh frequency, and these are called the Stokes lines or the Stokes lines, which is the smaller frequency or the smaller wave number. This is smaller wave number, and taking this much of the energy and de-exciting, your final state is E single prime. Now the third case is that suppose your scatterer is already in an energy state of E prime. If it is already in this E prime and it takes the energy of this h nu of c from the photon and it de-excited to the E double prime, then this energy is adding up. So this hc of nu plus of delta E means at the scatterer, after the scattering, it is gaining that energy of delta E. Means that once I will calculate that is the wave number corresponding to it, then I have this one, and total shift is delta E divided by hc again. Now your scattered photon having the higher energy, that is the anti-Stokes. That is the anti-Stokes lines for the Raman spectrum. Now this Raman shift, this shift is symmetrical, delta E divided by hc and delta E divided by hc, and this delta E divided by hc is my Raman shift for that molecule. And these are called the anti-Stokes line, these are called the Stokes line. And these are symmetrically situated with respect to this one Rayleigh scattering line having this wave number of nu. Since the number of the molecules are in the excited state, these are two states of the scatterer, excited states will be less. That is why we are getting the anti-Stokes line are the weaker. If you remember, in a case of the classical explanation, the Stokes line and the anti-Stokes line must have the same intensity. But exactly what we are getting that these anti-Stokes line are the weaker. The reason is that my scatterer is generally very few of the molecules are here in an excited state. This is why you are getting that the weaker lines in the your anti-Stokes portion. Now, this is the general case, is the generalization. Now, if you have a free molecule, as a scatterer, this molecule may have a vibrations and you may have a rotations. So, these stationary states E and E double prime, these are maybe your rotational states and you may have the vibrational states. If these are the vibrational states, then this phenomena is providing you the vibrational Raman spectra. If these are the rotational states, it is providing you the rotational Raman spectra. Now, before dealing that the rotational Raman spectra and the rotational Raman spectra and the vibrational Raman spectra, I suggest you just to go through the molecules symmetries, linear molecules, top symmetric, top asymmetric molecules, because most of the cases we are dealing the diatomic molecules which are the linear in the structure. So once you will be dealing that the asymmetric top and symmetric top, it will clear that for which molecules my Raman is effective and for such whose molecules we have this IR or the IR is effective. So then before dealing to that the vibrational Raman spectra and the rotational Raman spectra, I would suggest you just to go through the some of the symmetries of the molecules. Then it will be easier to understand that how this Raman effect is dealing for this my rotational spectra and the vibrational spectra. So for today's only I'm discussing this just a small discussion of the quantum theory of the Raman effect, and tomorrow I will be discussing that the rotational Raman spectra and the vibrational Raman spectra, and I would suggest you just to go through the sum of the molecules, and the material already have been provided to you, and just to go through that chapter 2 and chapter 4 in your that book, so it will be easier to understand that what exactly happening that we'll see that, and we'll see that how this my selection rules are important in the case of the Raman spectra, and once you are dealing with the symmetric top and asymmetric top, what are the selection rules, and that will be easier to understand that once we will be dealing that the this for the symmetric molecules, that is linear molecules, and banded, stressed. For we'll see that how these selection rules are changing, because in the case of the linear diatomic molecules, the selection rule for the rotation is delta Z is equal to 0 or delta Z is equal to plus minus or 2. On the other hand, you have a symmetric term, you may have the delta Z is equal to plus 1. That depending on the symmetry, because all over this Raman effect we are dealing that it is all about that the polarizability ellipse of the molecule. So the polarizability ellipse, how it is changing that its rotations, its orientation, it depending on its structure, and depending on its structure only, we are the selection rules are modeled. So just to go through these molecules, then it will be easier to understand for you. Thank you.